Swayam Prabha. Digital India. Educated India.
Welcome to NPTEL NOC, an introductory course on Point-Set-Topology Part-II. Today we will study some more examples of this S0, S1, S2 and so on. Actually we started seeing examples last time. They were all S2. So we will continue that. Here is one of the important example, the Hilbert cube. Consider the Hilbert space L2 over a countable family of set points. Namely, you can take the natural numbers. So recall that the space L2 consists of square summable sequences Si of real numbers, and the L2 norm there is nothing but take the sum of all the squares and then take the square root. For topological reasons, we will have a different look at this one. Indeed, we are now going to consider a smaller set here. Namely, let us start with the product of infinite countably many copies of the interval j, which is -1 to +1. So let us denote it by x. X is j power n. Okay. There are many ways to put a metric on it. So what we will do is we will use this L2 metric, L2 norm, and then there is a metric L2. So what we will do is we will take a standard embedding. Okay, the standard means it is convention after all. So a lot of people are using that, especially in analysis. So what we do, we take a point x here, which is xi, where each xi is between -1 and +1, right? So we will send it to x1, the second coordinate x2 will be divided by 2, the third coordinate will be divided by 3, and so on. The nth coordinate will be divided by n. So this is an arbitrary sequence of real numbers between -1 and +1. So this is another sequence. Now what happens? If you take the sum of squares, that is convergent. The sum is convergent. Okay, so this will be an element of L2. Okay, x itself is not an element of L2. It's easily checked that this map is a continuous bijection. Okay, it's a continuous bijection on the space. What is that? The image is all the coordinates modulus of xi. First of all, must be less than or equal to 1. I can't go out of that, but actually the ith coordinate should be in modulus less than 1 by I, because look at the image here. Xn is already between -+1. Xn divided by n is less than or equal to 1 by n. Right? So if you put this condition, after multiplying by I, it will be still inside -1 +1. Therefore, that will be a point of x. Okay, so that will show you that this is a bijection. All right, continuity of this one is obvious. So it's a continuous bijection. But actually, the way I am defining the ith coordinate, I am just multiplying it by the integer I. So even the inverse function is also continuous. There is no problem, which just means that this map phi is a homeomorphism of j power n into a subspace of the Hilbert space. That subspace we are denoting by this curly h and calling it the Hilbert cube. Okay. The notation may be different, but it is commonly agreed that this should be the Hilbert cube. Okay. The name is quite standard, but not the notation. Okay. So now without reference to h all the time, we can just write down the metric which is induced by this phi on x itself, namely given any point x and y inside capital X, distance between x and y can be defined to be just take xn minus yn, take the squares, divide by n square, take the sum, and then take the square root. Okay, so this is the metric. I don't want to write the norm here because X is not a vector space. Any space which is homeomorphic to Jn, tau d, namely what? The metric induced topology here, that is called a Hilbert cube. After all, we are doing topology, so anything which is homeomorphic to this is called a Hilbert cube. We are not very much particularly interested in the actual metric here, but only on the topology, and now we know that this topology is nothing but the product topology. Okay. So quite often it is convenient to think of this one as just j power n with its this h can be thought of as j power n with its product topology. Okay, this is all about convention and notation. The subspace QH of H of all points with rational coordinates satisfies S2. So this is what we want to say. First of all, it is a metric space. Now inside that it satisfies S2 is what I want to say. To see this, let Jn to J be the ith projection map, coordinate projection. Let P be any point in QH. Remember, QH is again all the coordinates of the points here will be rational. Okay, take any point in QH. Take an open subset containing P. Let V be a basic open set containing P, that's the open neighborhood, such that P belongs to V contained inside U. After all, every open set will be containing a basic neighborhood around that point. So neighborhood around that point, this basic neighborhood, will be of the form, by the very definition of the topology, product topology, intersection of finitely many pi I inverse of ui, where I, this ui is an open subset of minus 1 plus 1, the coordinate space. Okay, finitely many of them, so there will be a maximum n. I can include all of them up to n, no problem, right? Okay, but here I am going to choose this V such that each ui has this property, namely the boundary of ui, which will just consist of at most 2 points, depending upon where the point is taken. Okay, if the point is in the strictly in the interior, the boundary of ui will consist of 2 points. Both the points must be irrational. That means boundary of ui intersection Q is empty. Okay, this is done in the interval for each I up to 1, 2, 3 up to n. Then you take the inverse image of ui under pi I inverse, take the finite intersection. that is V. Automatically it will imply that boundary of V intersection QH is empty. See, this V is a subset of the entire J power n, or you can think of H, whatever, I am taking H. Intersection with QH is empty because the boundary point, at least one coordinate will be irrational, because here each of them has boundary irrational. Okay, here you have to use the elementary fact in product spaces, namely, if you have x cross y and a subset A of x, B of y, boundary of A cross B is equal to boundary of A cross B union A cross boundary of B. Use it again and again several times to go into the finite case here, finite intersection case, you will get this result. Okay. So that's all. For each point, you can choose a neighborhood such as boundary is empty means what? That neighborhood will define a partition, a separation of the point with the complement, mainly you started with U, right? They are separated out. So that is the property S2. So we have verified, we have got another example, namely subset of all points with all coordinates rational inside the Hilbert cube is also S2. Exactly similarly, we can show that IH inside H is also it's also S2. What is IH? All the coordinates of all the points are irrational. Okay, so you can reverse the role here, that is fine. In contrast, the subspace QL of all points whose coordinates are all rational in the entire Hilbert space L2 does not satisfy S2. Okay, so this is what we want to prove. Inside the smaller set, namely compact set, this H, this is working. But if you go to the entire L2, it's an unbounded thing, there S2 is not satisfied. Okay, so we will have examples of spaces which does not satisfy S2 also. Okay. So once again, how do you show that something is not S2? It suffices to prove that the boundary of any bounded open neighborhood of 0 in QL is non-empty. Okay, so at 0 you can prove that you can't have such a thing. You can't separate 0 by open subsets by closed subsets which do not contain 0, then over. Okay, so I am going to show that take a bounded open neighborhood U of 0, okay, then its boundary is non-empty inside QL, not inside L2 it's obvious, inside QL you have to show it's non-empty. Okay, so in other words, you take the entire boundary, intersect with QL, it is non-empty, so that. Okay, so this is done as follows. So let me show you the picture here first. So this is origin. Of course, my picture cannot contain infinitely many coordinates. So you have to think of this one as infinitely many, one at a time, something like that. So this is the origin. This is U is a bounded neighborhood of the origin. I start with on the x-axis, in the first one, a1 axis or x1 axis, I take a point a1, okay, inside U, maybe I don't have to take the 0 itself. Okay, take one point. Be sure in the inductive process I want to do that something. So be sure that this A1 is not far away from the complement of U. Okay, it's not far away from the complement of U. That means what? Let us say distance between A1 and the complement is a closed set. Let us say it is less than 1. Okay, this distance is less than 1. Next, I keep this first coordinate A1 moving to the R2. So keeping the first coordinate A1 as it is, I choose A2 so that this point is again closer to the boundary. So this was A1 I have chosen. So here I will choose it's 1 by 2. This I have 1. Here I will choose 1 by 2. So distance between A1, A2 and the boundary and the outside of the U complement is less than 1 by 2. How do I do that? So this is an open subset. Okay, so I keep moving inside this arrow. Okay, all the entire arrow may not be there, but there will be some point here as close as keep moving. Okay, having chosen A1, A2, an plus 1 will be chosen. First an, A2, an coordinates will be remain the same. The nth coordinate will be chosen so that the distance of this point to the boundary or to the complement is less than 1 by n. Okay, so that is what I am doing here. Okay, we will inductively we construct a sequence Pn. A1 0 0 0, A2 A1 A2 0 0 0, like that, A1 A2 An 0 0 0 of points inside U such that distance between Pn and the complement is less than 1 by n. It then follows, once I have got this one, it then follows that the limit sequence, namely A1 A2 An, okay, this P is actually in the boundary of U, because all these things are inside U, so this will be inside U bar, but its distance between this P and complement of U is 0, because it's less than 1 by n for all n. Therefore, this will be both in U and U bar and complement of U bar, so it is inside boundary of U. Okay, so how it is done, I have already explained it to you. Okay, so let me read that one. Consider the linear space P1, set of all xn belonging to L2, such that all the nth coordinate beyond that one are 0. That is the x1 axis, you can say. Clearly, P1 intersects both U and U complement. See, because U is bounded, because U contains the origin. So this line has to intersect U. Because U is bounded, it has to intersect the complement. So this is the property I am using. On that subspace, there will be a point inside U very close to U complement, as close as. This is what I have to use. So pick up P1, A1 belong to U such that distance is less than 1. Having chosen Pn, the same thing, look at Pn plus 1, it's all xi inside L2 such that the ith coordinates are all 0 beyond n plus 2. Okay, up to n plus 1 coordinates are there. Xi must be Ai as chosen up to nth. Okay, this subspace this is now just a line now. You see, if I fix up all the nth coordinates, only n plus 1 coordinate is free. So that line, okay, will intersect this point A1, A2, An. It passes through that, and it will go out of UC because U is bounded. So we pick up xn plus 1 equal to an plus 1 and take pn plus 1 equal to an plus 1 such that this distance. All that I have to do this one is intersect this line with u and u complement. So work inside the real line to get such a point. That's all. Okay, once that coordinate is chosen properly, distance between an up to an plus 1 and the new coordinate, so an and an plus 1 is depends only on this point, because you have to take ai minus corresponding ai, that this will be 0. Only an plus 1 square has to be less than 1 by n square. That's all. Okay, so that is done. So now we will have some theorems. Okay, so what we have done, we have shown one example wherein it is not S2 also. It is a metric space. It is an entire Hilbert space. So Hilbert space does not satisfy the QL does not satisfy the S2 property. Now here is a theorem. If X is Lindelof, then S2 implies S3. Remember that we have assumed that all our spaces are T1 right from the first lecture on this topic, right? But just to remind you, I have put T1 in the bracket here. Okay, if X is Lindelof, then S2 implies S3. The proof is somewhat similar to what we had done long back, maybe theorem 2.5, that a regular Lindelof space is normal. However, for completeness, we include the proof here. Okay, because we are not exactly doing normality here, nor we are exactly using regularity. Both are stronger hypotheses. S2 is stronger than regularity, S3 is stronger than normality. So let us go through this proof carefully. Take F1 and F2 two disjoint closed subsets of X. Then X is union of their complements because they are disjoint. Okay. Therefore, given X inside X, either X is inside F1C or X is inside F2C. Maybe it is in both, doesn't matter. One of them will be there always. Accordingly, choose a Klopen set Ux around X such that this Ux intersects Fj is empty. Accordingly, I have to do. If it is first one, see X is inside F1C, so I can choose Ux intersection F1 empty. If X is inside F2C, I will choose Ux intersection F2 is empty. So this is by S2. The property S2 assures you that such a Klopen subset exists. Okay. For each point I have chosen a Ux, therefore this X is union of all the Ux's. And each of them is open. X is Lindelof implies we have a countable subcover here. All right. Now we define a new family of Klopen subsets. Remember, these is open, they are both open as well as closed also. Okay. So how do I do it? Inductively. These kind of steps are same as what we have done in proving regular Lindelof implies normality. This step is same thing. V1 is U1, V2 is whatever you have taken, then V1, okay, you subtract that V1. So it is U2 minus V1. Like that, Vn will be Un minus whatever you have taken earlier, namely union of all the I rank 1 to n Ui's. Okay. I can write here Vi's also, because V1 is U1, V1 union V2 will be union U2 and so on. So you can do this way, this is also correct. Now what we have is each Vi is disjoint from other Vi, Vj. So it's a disjoint family. Each Vi is clopon. Why? Because being finite union, this is also clopon and this is clopon. Open minus closed is open. Closed minus open is closed. So this will be clopon. So each Vi's are clopon subsets, and we have written X as disjoint union of countably many clopon subsets. Moreover, each Vi, remember here what is the definition? Un minus something. So Vi is contained inside Ui, and hence Vi intersection Fi will be 0, because Ui intersection Fi is 0 for j equal to 1 or 2 accordingly. You don't know where they are coming from. There are two classes of them, right? Depending upon whether it is F corresponding Ux, Ui corresponds to one of the Ux where X is inside F1C or inside F2C. Okay. The entire family of VIs is divided into two families accordingly. Okay, according to whether Vi intersects Fi, okay, I equal to j equal to 1 or 2 is must be j. Vi intersects Fj is non-empty. Now take W1 to be union of all those Vi's such that Vi intersection F1 is non-empty. Okay, and other things are W2, namely all the Vi's which Vi intersection F1 is empty. So I have taken all the Vi's here. Some of them are here, some of them are there, and they are disjoint families. It follows that X is a union of W1 and W2. W1 intersection W2 is empty because every Vi here and Vj here, they don't intersect. Being unions of clopon sets, W1 and W2 are both open. That is enough actually. They are clopon also. And F1 will be inside W1 now. Okay, because F1 does not intersect any of them. But F1 is contained in the union. So it must be inside W1. And F2 by very definition has to be inside W2. Okay, the rest of them has to be W2. Okay, so what we have done is writing X as disjoint union of two open sets. This is a partition. This is a separation now. Right? F1 inside W1, F2 inside. So that is the property S3. Okay. In conclusion, we know that a Lindelof T1 space S2 implies S3, but we have already proved S3 implies S2 as soon as it's T1 space. So these two are equivalent. However, even if X is a separable metric space, the three of them here, earlier one, S0, S1 and S2, they are inequivalent. Okay. Proof is not all that easy. In a T1 space, we have seen that S2 implies S1 implies S0. So you assume it is separable metric space. Even then you can't go back in these arrows. That is the meaning of this word. Okay, so we will have examples finally. So here is one example which is not a metric space, okay, but it's an easy example. Start with a countably infinite family, infinite set with a discrete topology. That is my n tau. Now take extra points A and B. So n disjoint in A and B, that is my x. Okay. Now I want to put a topology tau hat on this x. Okay, this will consist of all the members of tau along with all subsets y of x which intersect AB and such that x minus y is finite. Intersect AB means they should contain either A or B or both. Okay. But then the complement of that y inside x must be finite. Okay, check that this definition makes tau hat a topology on x. Not very difficult. This kind of thing we have done several times now. For each x, if x is inside n, then it is discrete topology, so it is both open and closed in x. Because all the open subsets in tau, they are inside tau hat also. So they are all components. If a singleton set is both open and closed, that estimates must be component, right? Any subset larger than AB is disconnected. Can you see that? Take AB itself, okay, as a subspace of n, as a subspace of x. What is the topology on this one? As a subspace, it is discrete space. Okay, therefore singleton AB itself is disconnected. Therefore anything larger than AB will be also disconnected. So this shows that this topology tau hat is totally disconnected. All the points are singleton points are components. All the components are singletons. Okay. However, this is not a T1 space at all. It's not even a T1 space. Why? Because take any neighborhood of A inside X, not AB. AB if you take as subspace, that is discrete. But A and B as elements of tau hat, any neighborhood, the complement is finite. Any neighborhood of B, complement is finite. N is infinite. So A intersection, that U intersection V will be non-empty. So that is similar to this cofinite topology. Therefore, this is not a T1 space. So this A and B are there just to make it non-T1 space. Okay, but this is totally disconnected space. That is the reason we don't want to study such anomalous examples. That is why we are putting assumed T1ness right in the beginning. Okay, so I have repeated it here. So the same thing will tell you that, of course, it is not Hausdorff either, because neighborhoods of A and B are not disjoint. In particular, it does not satisfy, sorry, this is T1, but it is not T2. Okay, I want a T1, still it is not good. That is the whole idea. Hence, X is not Hausdorff. That is the point. Because members of open subsets around A and open subsets around B, they always intersect. Okay, if it is not Hausdorff, it cannot be S1. S1 is stronger than Hausdorffness. Okay, so it is a totally disconnected space which is not S1. Next time we will have within the metric spaces such examples. But for that we have to work very hard. But this is a very well known example in topology, Knaster-Kuratowski example. Okay, so that we will study next time.